This converts back losslessly. Not only does it convert back losslessly, it also has the noise removed. Oh boy, this is going to be a fun one, isn't it? If you're curious about what's going on here, there was a challenge posted by Neuralink a few days ago. Neuralink is the company that Elon Musk is working on for attaching a sensor to your brain to get data out to do things with it. It's currently been put in one person who doesn't have the ability to move their body due to an accident. They're fully paralyzed minus a little bit of movement in their head. And through the Neuralink implant, they've been able to move a mouse cursor, play chess, if I recall, they were playing a lot of Sid Meier's Civilization, and they're hyped as can be to have control of things again that isn't just them using their voice. And I don't want to talk any shit on this technology because it is revolutionary. It is honestly kind of cool that Elon is putting a ton of his money into something that for the foreseeable future is only ever going to benefit people who have physical disabilities, because there's nothing worse than not being able to use parts of your body. I had an accident before where I was not able to walk for a while, and it is traumatic in ways that I can't really put words to. And the fact that Neuralink is putting so much effort, engineering cost, financial support, and all of these things in to make it so people who have the inability to use parts of their body to have other things to control instead is awesome. And I want to give that massive props, because I honestly don't think Neuralink's going to go much further. The people who are going to be interested in this are people who can't use their arms. But if you can't, also this is happening. This is all coming up because Neuralink posted a challenge. They need ways to get the data out of that chip and two other things really efficiently in terms of the amount of bandwidth, but also really power efficiently because they don't have very much power when they just put something in your head. So how can they get this data out effectively? They clearly don't know and have put out a public challenge. Neuralink Compression Challenge. Here is 1 hour of raw electrode recordings from a Neuralink implant. The Neuralink is implanted in the motor cortex of a non-human primate, and the recordings were made while playing a video game like this. Compression is essential. N1 implants generate around 200 megabits per second of electrode data, which is 1,024 electrodes at 20 kilohertz, 10 byte resolution. This is important. Remember the resolution here. And it can transmit wirelessly. So we want to compress this around 200x, and it has to be able to be run in real time and at low power. That is a big challenge. They aren't pretending it's not. So I say 10 bit, sorry. The 10-bit resolution is important. 10-bit resolution is a key piece here that will be coming up as we go along. Here's a spectrogram showing the signals and what is included in it. Neuralink started a compression challenge. They're asking for people to find methods to losslessly compress files to 1/200th the size, but the files are extremely noisy, so that's certainly not possible. Yeah, there's a lot of noise going on in these files. The issue here is the word lossless. Is the word lossless even included in this proposal? Okay, this is kind of silly that they expect you to run their check to make sure the compression is lossless. Okay, this is good info, and this is where things are going to start getting silly, because the word lossless is a questionable choice of words in a lot of these places. And the reason people are outraged here is the use of the word losslessly and also has the noise removed. Before we can go any further, we're going to have to do a little bit of explanation around conversion, compression, and what the word lossless actually means. Signals, in this case, we'll say sonic signals, so like sound, comes in waves. Here's a really nice, crude wave of sound. Waves are analog. They go up and down at various rates, but they're not fixed. They're not perfect. They're not exact. They are in flux. The same way that, like, if I took a picture of my door, it might look very close to my door, but there are things that you can see in reality that the camera can't capture, be it certain colors, be it certain things that are too small. You can't just represent the physical world digitally perfectly. That's not reality. As such, we need a way to represent this. The way that most waves are represented digitally is by keeping track of the point the wave is at various locations. So if we want to represent this particular wave, we can make a bunch of effectively rectangles that say, at this point, it was this high. At this point, it was this high. And the data that you're collecting here isn't the trajectory of the wave. It's at this second, it was however high this is. Like if we say that the bottom here is 0, and we'll say the top here is much louder. This is just one dimensional, by the way. Once you add multi-dimension, this gets way crazier. We'll say this is like 100 dB. Then as we go through over time, we say, okay, we start at 0 dB. Then at this interval, we're at 5 dB. Then we're at 50 dB. Then we're at 75. Then we're at 100. Then we go back down. The way this changes over time is represented by taking snippets, effectively, taking segments over time to represent the individual moments in time. There is no such thing as true lossless going from an analog signal to a digital one. So when I do something like snap my fingers, that's not ones and zeros in reality. It gets represented as ones and zeros once it goes through my mic as a wave, as a signal, and then gets to my amplifier, my interface, that takes that signal, boosts it, filters it, makes changes to it, but those changes are all happening digitally at that point. So once it has the signal, it has the ups and downs of the waves that I'm spitting into my microphone, then it turns that into ones and zeros. It turns that into data that it can then do things with. The conversion from analog to digital is inherently lossy. If you have a vinyl, which is an analog medium, because you're actually cutting the grooves of the sound wave into it, rather than saving it as a file that's ones and zeros, because of that, a vinyl can be a lossless recording and representation because it takes those waves and it perfectly encapsulates them in a disc, a physical thing that isn't ones and zeros. There is no way to losslessly encode a vinyl if it was recorded in an analog fashion. This means that if people are taking digital recordings that they record on a computer and pressing them on vinyl, they're stupid and silly. It also means if they're saying that their encoding of their vinyl is lossless when they put it through their magic digital thing, they're also silly. But they're both being silly because going from analog to digital is always lossy, some amount. That's why we can upscale old film from like the first 3 Star Wars movies, 4 through 6, but we can't upscale the digital ones anywhere near as well because 1 through 3 were recorded as ones and zeros, not as light going through a piece of film. So as great as the digital world is, it is inherently a lossy move to go from analog to digital. These details get important as we go along. Another important thing to know as we're representing these things digitally is the idea of sample rate. So right now we're sampling, let's say we'll call from here to here, just to make it simple, we'll say from here to here is 0 seconds to 1 second. Obviously your sample rate will be much bigger than this in reality, but we'll pretend that this first section is 0 second and this one's 1 second. Our sample rate is 4 samples per second because we have 1, 2, 3, 4 samples occurring within the second. Usually you want significantly more than this, like hilariously more than this, but just as a sample, we have a sample rate here of 4 per second. Let's say we want this file to be smaller. Right now, we have these different numbers all representing things here. Easy way to make this smaller? Just delete 2 of them. It's no longer going to be as accurate a curve, but hey, at the very least, we have cut the data down a bunch. But if you want to then upscale this back to the way it was before, that's where things start to get a little rougher because as great as this can be, and this is how things like MP3s work, by the way, if you're curious, is we're changing how often we sample things. We also might cut down the range. Like right now, we can go up to 100. What if we just lower this? And what if we raise this? What if instead of 100 to 0, we said like 75 dB to 15 dB? And now anything that's below this just gets cut off, so we delete that. Now this can be way smaller. This can be way smaller. And this can be way smaller too, where the top's just chopped off there. Now we have way less data to encode. Every sample can be represented with a smaller amount of data. It's way better compressed. However, we've lost all of the data that existed below, in this case, 15 dB and above 75 dB. This makes sense in certain places, but not necessarily in others. If we look at something like the frequency response charts, these charts are interesting because they're in the range of the lowest to the highest sounds. So 20 hertz is the lowest sound humans can hear. 20,000 hertz is the highest sound humans can theoretically hear. Most humans tap out much earlier in the like 14-ish thousand range. And depending on how much hearing damage you have, it might be way earlier. But this range is what we can hear, which means if you have things in your music files that are below 20 hertz or above 20,000 hertz, your dog might be able to hear it, but you can't. So we can just safely lob those off. Now we have way less data we have to encode. If we want to go even further, well, most speakers can't play below 100, and most people don't even want to hear over 10,000, so we can shrink the range even further. Now we have a much smaller set, maybe 100 hertz to 8,000 hertz, that is way easier to encode. All of these hacks are how we ended up getting things like MP3s and audio streaming to work by reducing how much of the data we actually bothered to encode in the first place. That's awesome. It means that you're going to get worse audio quality. So if you have like a really nice subwoofer, you're not going to be able to hear a lot of the things that the subwoofer would play. And if you have like old audio bounces, like old Soulja Boy tracks, before you knew how any of this stuff worked, A lot of those were exported as a really low bitrate MP3, so they sound awful on a nice system because you don't get these low sounds that your subwoofer might need. Why am I talking about subwoofers and all this stuff? Well, I'm an audio engineer. I'm going to take any opportunity I can, but we're not here to talk about audio in the traditional sense. We're here to talk about audio as a signal. What if this wave wasn't actually being used to represent sound? Let's go back here for a second, because while the inputs here are absolutely analog sound waves that they are recording, they don't want to play it back. Their goal is to find some data that was encoded here. It's actually kind of the opposite of what we were talking about before, where I was showing that if you have an analog signal, making it digital is never going to be perfect. But what if we have a digital signal and we want to make it analog? Sounds crazy, I know, but you're also watching my video right now, which is almost certainly coming through in that way. Most of the internet, especially in the United States, is coming through copper pipes that are analog pipes that are used to convert analog signals and waves that are sometimes so high or so low pitch we can't hear them or see them through these things as an analog format, so that then when they get to the other side, we can convert it digitally. Or if you're on Wi-Fi, Wi-Fi is a wave that we can't see going from your router to your device, and that is an analog, real world, real physical world wave that we then have to convert into a digital signal when we get it. But it's a digital signal from the start. So if we represent it, like we have, let's say 10010, here's some binary. So we'll say 1 is up and then 0 is down. So we say down for a bit, 1, 0. Cool. So here's a rough representation of what this might look like as an analog wave. And now your device has to receive this. And it goes through a thing called a digital to analog converter that then re-encodes that back as this value. The important thing to note here is that despite there being this analog thing in the middle, what we wanted is the 10010 that we put in initially. This is where things start to get fun, because it doesn't matter how well we can compress this. If somebody was to say, compress this, make this smaller, there's so much data here. Look at how like this slightly curves. Maybe we have the like floor for 0 is here and the floor for 1 is here. Why do we capture that data? Why do we capture the slopes? Why do we capture what's under here? Why is there all this stuff going on down there that we don't care about? All we care about is the 1, the 0, the 0, the 1, the 0. When you're measuring lossless, you don't want to measure the lossless part of the signal. You want to measure lossless relative to the thing you actually want, which is the digital representation of the input. This is where things start to get really fun, because with the Neuralink case, they have specific bit depth, specific information, specific stuff going on with the chip that they want to get out of the chip and to another thing somewhere else. The protocol here is not what matters. What matters is that the data going in can be as minimal as possible, so you can encode it as simply as possible and then get it out on the other side. This is a whole field called signal processing. How do we encode signals? How do we encode data into signals? How do we transfer it? How do we get it in and out fast? This is how Wi-Fi works. This is how the internet works. This is how everything that isn't a fiber optic digital cable works. And even then, the fiber works by flashing lights on and off really fast with an analog, so to speak, signal. This is what I really want to drive home before we go further, because we need to understand the basics of this before we go back here to the not only does it convert back losslessly, it also has the noise removed. This is a dumb tweet. I even called him out accordingly. How do you feel about your use of the word lossless in the original tweet? I should have clarified myself more, but then I wouldn't have gotten to have so much fun. Run into the ground, though. It's good entertainment. Thank you, Moderate Rock, for the blessing to make this video. It's going to be really fun. But when you're measuring lossless, you need to determine what you're trying to encode. Because if I wanted to measure lossless based on this signal, that's going to be measured very differently from measuring lossless based on this guy. There's something a little controversial, but might be biased from my audio background. Generally speaking, when I hear the word lossless, it's being used to describe something in the music world. So if something was recorded digitally, it was recorded in a professional studio used to make music, and they have a recording that's a certain quality level, and then they put it on Spotify, Spotify is going to compress the shit out of that. So if you want the highest quality possible audio based on the way it was recorded, you're looking for a lossless audio format. The most popular one is FLAC. Wave can be lossless as well, depending on how you encode and record in the first place. There's a lot of standards now for lossless audio encoding, which means that the thing that existed in the studio, the digital file there, is as close as possible to what you ended up getting when you listened to the music. Some people can hear it, some people can't. It doesn't matter though, because if you look at it in a spectrogram, you actually look at the way the audio is being decoded, you'll see with an MP3 that you have a smaller range with less sound. And if you listen to it with FLAC or decoded a FLAC that was encoded properly, you'll see a way wider range of sound being captured. That said, if the original recording was a crappy MP3, no amount of FLAC magic is going to make it better. You can have a lossless encoding that is an MP3 as long as the original thing you're re-encoding was less lossy than what you're doing there. Lossless is defined as much by the input as the output. And that's where I think the problem breaks down here. Here's a weird analogy. If I had a really crappy quality MP3 and I recorded that with my fancy microphone, my fancy gear, all of that as a FLAC, I still have a crappy signal coming out of my speaker though. So I have a really low quality speaker playing a really low quality audio file, maybe 20 kilobytes per second. The speaker plays that audio out to my mic and I record that losslessly in a much bigger, let's say like 20,000 kilobyte per second file. What's a better representation of the original? Is it my lossless recording or is it the original file we played through the speaker? Because if your goal is to represent the highest quality version of the original audio, it's going to be that crappy MP3. But if you want as much data as possible, you want to capture not what that specific MP3 was, but the experience of listening to it through your speaker. Doing it with the recording with the microphone makes more sense. But where lossless is defined by where you start and stop counting the inputs and outputs. And I think that's where things really fell apart here, because everyone who read that tweet, everyone who had an opinion, and even Neuralink themselves seem to have their own different definition of lossless in terms of how we're processing signals here. To go back to the tweet I had here, the use of the word lossless in Neuralink's compression challenge is silly because there is so much noise in their data. There is just so much going on here that isn't necessary if they're just trying to capture that 10-bit signal. So what if we just don't capture all that? What if we ignore that in our encoding instead? Yeah. For a comparison, for those who aren't familiar with spectrograms, here you could see actual useful spikes where things happen. You can see where someone's talking and where they aren't based on the signal that we have here. This one's just straight noise. It's much harder to see the signals. So ideally, we could find a way to get the signal data out, usually by amplifying or tuning the frequencies here to get the data we want, and then we do the encoding after. I want to check the eval sh quick. Mark said that this is literally just like a diff, but I want to confirm. Yeah, this is silly. They're just checking the diff, and if there is any difference between the files after, they shout, which is again silly because as we saw there, the wave file they give you as the example doesn't have much data. It's utter nonsense. Let's just take a look at it. I'm so curious. Yeah, it's all wave files, which again is a sound file. So all of these files have these signals, have these, as they describe, 10-bit resolution signals, but they're encoding them as a wave audio file full of noise and signals that are entirely useless. Okay, Nate in chat's making some good points. If they don't have a predefined signal because it's brain waves, then if the input is known, then what I'm saying makes sense. But if you don't know it, then because your brain isn't strict about what it transmits, then it's nice to have all of the signal. Yeah, but most of the signal is literal garbage and probably is useless. Where's the original signal that he showed here? Pre-normalization. Because like in any signal, the thing that matters isn't the level at a given time, it's the difference between levels. The difference between levels is where things start to fall apart. Like if I measure every single point along this line, I'm fucked. If I measure how far one line is from another, that is both more useful in terms of the signal, but it's also much easier to compress because it's smaller numbers throughout the entirety of your encoding. It makes life significantly easier. But if you don't actually know, like if theoretically it turns out we're wrong, and what matters is actually the difference between here and here, and not the difference between here and here, yeah. And since it's brain data, we don't theoretically actually know where in this spectrum, where in this range, where in this signal, the actual useful signal is. Sure, but almost always the useful signal is the gaps between things, not the actual specific values within the given thing. But technically, the origin isn't digital because it's brain waves. But what we have here isn't the brain waves. It's what the chip gets from the brain waves. This isn't a recording of the exact waves from the brain. This is the chip getting the brain waves and then putting them in a file. So it already is a lossy representation. If most of the signal is things moving constantly back and forth in this range here, like if this is the area that your signal is in most of the time and you're capturing every tiny bit here, that just sucks and it's impossible to compress that. It's lossy in the sense that relative to this wave, we are missing some of the data, but it's lossless in the sense that if we're actually tracking the ranges as they're entered and left, we have the exact binary, so to speak, ones and zeros bit data from this instead. I want to read his thread though, because that seemed to have a couple entertaining bangers in here. Okay, now that I've stitched the files back together in context, can I remove the noise or are you guys going to get mad again? Doesn't matter. I'm doing it anyways, full scale, fun. So if you're not familiar with what he's doing here, it's called normalizing. He's also doing this, I'm almost certain, yeah, he's doing this in one of my favorite programs, Audacity. Audacity is an audio editor, which you use for fixing, stitching, changing, and fucking around with audio stuff. Really nice program. I use it for my audio on my videos for a long time. It's free, open source, and dope. Normalizing is when you take some audio that has a wider range of levels and get them a little closer together. Usually you're pushing them up. So if I'm talking and my audio level's at negative 10 dB, but I want it closer to like -5, I can normalize at a different true peak and it will bump everything up. So the loudest points cap there and everything else gets bumped up accordingly to balance it out. Oh, this is Reaper? Damn, my bad. I did not know Reaper looked like this nowadays. God, yeah, these signals are awful. Okay, so we know that there's already a 1 kilohertz filter on the data because we saw it on the analyzer earlier. So first, let's try a better one. Having a bit of a brain fart, I just wanted to try an FFT peak filter. I have set the middle frequency to 1 kilohertz and the low frequency at the longest brainwave frequency, which is 0.5 hertz. I doubt the ADC even goes down that far, but let's find out. Actually, that does reveal the signal quite a bit. It kind of sounds like an ultrasound machine. You'll also have to take my word for it. Straight LPF gives you the complete waveform, but it's low frequency information, and I don't have headphones at the moment to actually listen to it. However, it does make the noise inaudible, so I was right. It ultimately doesn't need to be there. Interesting. Whether or not it needs to be there in the first place, I can't definitively answer, as I don't know exactly what filter the system uses to process the information. Here we're getting a little into like crazy way of thinking things, like the idea that you can tell which signals are useful by being able to hear them is a little funny. But at the same time, if the point he made here, which is that the input already has a 1 kilohertz filter on the data, they're already filtering the data too. So the chip generating this data on the brain is already arbitrarily filtering at a floor and a ceiling. Ideally, we would have an idea of which data is and isn't valuable before we get into this war, but here we are. Let's take advantage of it. Armed with this information, we can design a lossless reconstruction algorithm, which takes distorted data and restores it in relation to the original signal before capture. This is the key. This is the thing I really wanted to drive home, is that our goal is to be as close as possible to the thing that went in, not the thing being transferred. If the goal is to have the best data relative to what we input, we shouldn't be comparing the wave file generated by the chip. We should determine what the input was or what represents it, and then see how we can get something as close as possible to that later. I'd make the argument that the word lossless is effectively meaningless here because we already have loss as described above with that filter. So the input signal's already lossy. Now we're determining how much loss we're okay with and what loss does and doesn't matter. I vaguely remember the max amplitude of the files being -25 dB peak originally, so we'll gain +20 to -5 dB. So this is bumping up the decibels because it's such a quiet signal that it's harder to encode. But if you bump it up, much easier to deal with. And also you can see it and hear it, and you can actually get something out of this file now. Cool. Currently, I am testing an adaptive spectral noise remover with a buffer of 5 seconds to see if the SNR can be improved digitally. Signals improved, but there's a few harmonic peaks showing up. Very interesting. Now that's what I remember EEG waves sounding like. You can clearly hear the signals and not the noise. Beautiful. Zooming in gives us a nice centered waveform with data clearly on both sides of the zero, crossing points, which is what you want. Yeah. Part of the data all being useful is that we have a zero. We have an off so that we can show what on is relative to that. And this data actually looks useful now. At this point, the signal should be fairly usable. The applied signal processing in order is we sequence the files into linear timeline, we normalize to the peak sample, then we spectral denoise the sample that we have to get rid of these little tiny static bits of things moving around unnecessarily, so it's way easier to encode. You can probably process it further, but it is a data signal and it doesn't matter as much. Again, important, it is a data signal. We're not trying to perfectly represent the waves, we're trying to get as much data as possible, which is represented by ones and zeros in the end. Since we have the complete corrected waveform, we can now apply bitrate reduction and compression to lower the file size. Just going to start with 8 bits because there's only 6 there anyways. Lol. So this is with a FLAC. So it's a FLAC. It's lossless, right? Clearly, lossless, FLAC. That's how it works, right? Way too much compression with the setting. The HF data is just busting out of the peaks. I think I might want to switch the processing order around. Compressing after noise reduction seems to create a high amount of artifacting. Likely and true. Here's a 58% effective compression rate compared to the original 63 megs. Now retesting with the noise reduction. While it's running, I would like to float the idea of perhaps stitching the files together before you apply your compression algorithm. It might give you a wider range of data to pack per byte. They are sequential in both time and file name, so it should be an easy script. I don't love this idea because the point is that it runs real time. So this is kind of, again, defying the expectations that are presented in the challenge here. Because the whole point is that as the signal's captured, it can compress and send it. Not that when you have hours of data that you can compress it all at once. Doing NR after compression worked a lot better. Oh, look at that signal. You can actually clearly see things going up and down and not a bunch of fucking noise in the way. Isn't that nice? File 2 is the wave output from the normalized and rendered stitch file. So here's the compressed. Here's the original. Tried to line them up. Didn't get it just right. Looks pretty good, though. Running the file again gives us 24.1 megs. Cool. Shadow Hill's mastering compressor. You're compressing brain waves. I love that. Audio compressors don't actually improve these kinds of signals. Good. Thank you for pointing that out. Now for the benefits of the comp sci people, this is not lossless compression. This is lossless signal restoration. The goal here, again, is to get the signal that was put in initially, not to perfectly represent the exact data file here. This clearly defies the admittedly stupid requirements that Neuralink put out here. Using the word lossless here is stupid because this signal is not something you can meaningfully compress losslessly. Like this is like the Pied Piper algorithms, what they're looking for here. Some magic folding of shit to fix all of our problems. That's not reality. And I think Moderate Rock is much less a CS person and much more a hacker in the hardware space, the electrical engineering space. Like if you told an electrical engineer to losslessly compress the signal of some random chip on the board putting out random shit, they'd be like, do you mean what we put in? Or do you mean the actual signal that it's generating? Because one of those makes sense and one of them is stupid. Anyways, but now you should be able to see what kind of compression ratios you can get with signal-dependent compression. I was able to get the file from 63 megs to 24 megabytes, but not without converting to 8-bit, having the bit rate, and truncating extra noise. All this information should help anyone looking to do the task for real. Enjoy. I don't think you're going to hit the target. There's too much noise, and I still feel like more signal conditioning is warranted, especially between clips. The data path still needs improvement, especially if they're trying to capture low-frequency data at low power. I don't know exactly what ADC they are using, but they are most likely limited to 1 volt for power, I hope. If there's more than 1 volt on your brain, I'm scared. Picking a random one that sort of matches the data spec we get is, here's a random chip people put on brains, supposedly, and here are the signals. Cool, they show these numbers. This is beyond my pay grade. As a hardware engineer, I would like to point out to the software people that from my POV, a 10 to 20 kilohertz file is already extremely lossy relative to the input signal, so I would want to ensure that this initial signal path is as clean as possible. Again, I've been pushing this. This is where my software dev side and my audio engineering side get angry at each other, because lossless is a silly word that's incorrectly used on both sides, and now we're all going to go insane because we think lossless is the exact thing being represented digitally. He thinks the thing we're starting with is already lossy, so why the fuck do we care? A more convenient and compact solution to a discrete DAC, again, digital to analog converter, is to use a codec like this one, but it would depend on the space requirements. An OEM like Neuralink, though, would have significantly more options because you can order custom chips to your exact specs. Oh wait, we were arguing whether or not there was hidden data in the noise floor. There isn't any room in the data to hide signals in the noise floor. The noise is just noise. However, there are phase correlations between the noise and the signal due to the even frequency distribution. So combined with the poor signal-to-noise ratio and the low input volumes, you don't want to remove too much of it or you'll affect the frequencies in the signal itself. Another good point. The noise, the random jumps up and down all over the place in small ranges, those are so frequent in this data that if you get rid of all of them, it'll affect the actual spikes that you care about. So if you go too crazy with it, you're screwed. A couple more opinions I want to bring in here. I think they're valuable. This banger. I have a master's degree. I usually break up weed on it. We see you, King. This was great too. Never seen so many midwits dunk on a guy who's obviously correct, making him the main character but actually embarrassing themselves. Let's take a look at these. Okay, I get where you're coming from. It's mostly high bitrate signals too. Maybe in the end, we lack context of how scientifically proven good brain signals actually look. Since what if these noises actually have some important impulse data? I can't say for sure if the signals captured are accurate because they are so distorted they are pretty much unusable. But I can say that everything from 1 kilohertz and up is below the entire dynamic range of the ADC, so the high frequency information is irrelevant. The actual signal is PWM. Yeah, pulse width modulation, if you're curious. But the fact that there's all this data above when the actual chip can only capture up to that point means you can and should just trim all that off. Have you shown the idea to the Neuralink team? Perhaps they'll be able to give the final verdict on whether or not what you removed is important or not. I don't actually care what they think since they weren't forward-thinking enough to not put a 6-bit signal from a 10-bit ADC into a 16-bit container and then ask for software solutions to fix their bad hardware design. For what it's worth, this is the tweet where I came around and was like, okay, this guy absolutely knows what he's talking about. Let's see you put 16 pounds of crap in a 4-pound bag. Brother, they are trying to compress what's likely to be brain signals. How do you not know, or how do you know which signals are important parts of functional body impulses and what aren't? Like what you're trying to do in compression with noise removal is appreciated sometimes, but not with this one, I think. Because ADCs have a functional sampling limit. Again, the input, the thing going into the ADC, has caps on both sides. Okay. I have a sinking feeling that Sean here is a software dev. Twitter, Sean Dre 0101. Even better. Even fucking better. Certainly a software dev. I think we can safely confirm not only is he a software dev, but he has great opinions about software and clearly knows exactly what he is talking about. Yeah. Those are the types of people who are fighting with this guy. I've been an audio engineer and hardware designer for the last 15 years, so my approach is always to optimize the signal before you capture it so you have the least amount of post-processing to do. This work comes with a lot of staring at different waveforms to find noise. I have done this enough, even just for content shit, that I very much sympathize, and I can also sympathize with him being annoyed and memeing the shit out of people who just don't get it, that think lossless is data in, data out, not recognizing the reality of signals. They should not have used the word lossless. Anyone using the word lossless here just doesn't get it, but that's Neuralink being stupid and that guy being nuts too. But yeah, there's a lot of good memes about this. I'll be real. Like the code is faster if you put the comment signal in front of every line, which greatly improves compilation performance. Hopefully you guys understand why that's stupid, but also raises the point that like software devs don't get this. And when they compare it to software things, it looks silly. All these people pushing cubes, this guy found a much faster way by shaving things off. Yeah, if the goal is to get whatever's inside the box across, this makes a lot of sense. But if the goal is to get the cube across, doesn't make sense. Very funny meme because it shows both the correct and incorrect case here. Look at my compression algorithm. The image on the left uses a ton of data, but the image on the right only uses 3 bytes. Not only is the compression lossless, I removed all the noise as well. Funny. And look at their reply too. By the way, yes, 200x compression lossless is ridiculous. Yes, the data is 80% noise. Yes, he probably did remove only the noise and proper data. However, I am capable of admitting that I am wrong, so I will say that this is still not lossless compression, but lossy. However, lossy compression in the way OP did, with lossless on the bits that actually matter, makes much more sense for the challenge, and the people who wrote the challenge are probably just as dumb as me. That's a phenomenal summary of what happened here, and I appreciate you for that one. The noise is not the data. Aw, you're sweet. The noise is not the data. Hello, human resources? This is another person who did the challenge and got a lot of positivity for it, even though they, again, are compressing and they are making things lossless because they truncate to 4 bits to cut off the noise. And if you subsample from 20 kilohertz to 400 hertz, you end up with way less stuff. And now you can compress the signal to 200x in 10 milliseconds chunks. The alternative is to run some kind of triggering system in the loop and transmit bits for spikes. 4-bit sampling, 16 levels, preserves the signal, so the things that actually matter, which are the spikes. It's almost no difference looking at FT truncation. Across the whole sample, which is 100K data points, 700 frequencies are heaps. Yeah, the vast majority of the things in here are useless. All the garbage in the middle is noise. What we care about is the stuff here and the stuff here. So yeah, throwing all that out makes things significantly easier. Cool. But when this guy said it, everybody was cool with it. And I will end this one with a good summary reply that explains why everybody was mad, why this all happened, from a specific legend who I dearly love, Math Geek. Math Geek will never qualify themselves, so I will for them. Math Geek is Krill on YouTube, and he is one of my favorite channels on YouTube because every year during the Advent of Code era, he does Advent Code, which, if somehow you don't know and you're here, is a code challenge where you get a programming problem every day from the 1st to 25th of December, and he competes every year. The reason this matters is because he does Advent Code in Excel. I am not joking. He completes these complex programming challenges via Excel. It is nuts. There's nothing else I've ever seen quite like this in the programming world. These problems suck. And to abuse a piece of software like Excel, to take these arbitrary, absurd inputs in and get actual working like input or like values out of it is a work of art. And not only does he do this, he actually gets leaderboard spots relatively regularly. Like he has hit the top 1,000 far more often than I would ever like to admit. Here he was a top 500 in the world on day 7, doing it in Excel. Here he was top 500 for the first half too, which is even more cracked. Like 126. On the first day, he was in the first 200 people in the world who solved the problem. And no, he's not using Visual Basic or any of the like code features in Excel. He's just using formulas and transforms to get these answers in hilariously short amounts of time. It is a work of art. He is surreal and is one of those people that just knows numbers and math and spreadsheet type shit better than anyone else. And you should definitely give him a sub if you are interested in that, at the very least, to watch during the Advent of Code era. Krill's a legend. I have massive respect for them. MathGeek007 on Twitter perfectly summarized the issue here. The data has a bunch of noise, so 200x compression isn't possible. He's all right. He's not trying to pretend this is something it isn't. The reason people are upset is the use of the word lossless, specifically the phrasing of, not only is it lossless, I also removed the noise. That phrasing is what people have issues with. That phrasing is what I brought up here. How do you feel about your use of the word lossless in the original tweet? He said he should have clarified, but it wouldn't have gotten to be so much fun otherwise. Run it into the ground, though. It's good entertainment. I hope this is entertaining for you guys as well, because I certainly had a lot of fun covering this one. Finally getting to use my audio degree for something, and yeah, nerding out about signals processing in Lossless. Let me know if you learned anything in the comments. I think this was a shit show, but at least it was a fun one. Until next time, peace, nerds.